Okay, today we're going to talk about Newton's laws of motion. For our purposes, we're defining motion as a change in position of an object when compared to the object's starting point or previous position. So something has to move from one place to another for it to have motion. We have here, this is Isaac Newton. Isaac Newton lived from 1643 to 1727, and he described how all things move on Earth and in space. His first law of motion, so he had 3 laws of motion that he's famous for. The first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion, unless acted upon by an outside force, or a different force or an opposite force. So to simplify this law, let's break it down into 2 parts. So let's look at the first part. An object at rest will stay at rest, unless acted upon by an outside force. So if we have a book sitting on a table, that book will not move from its position unless a force, and in our illustration here, that's a person's finger, is applied to it, causing the book to move. So we could put a book on the table in a room, walk out, shut the door. We could come back a year later, and the book would still be in the same spot. And then an object in motion will stay in motion unless acted upon by an outside force. So here we have the book is sliding across the table. The force of friction acts on the book to slow it down and bring it to rest, right? Because we know that if we slide something across the table or across the floor, it's not going to stay moving forever. It will stop, even a ball. And that's because friction is acting upon the object. So here's an example of Newton's first law in motion. In this animation, both the car and the person in the car are in motion. They're moving. When the car hits the wall, here's the tricky part, the wall is applying the force to the car, stopping its motion, but it's not applying the force to that person. So he's continuing to move, he's continuing in motion, until he's stopped by an outside force. In this case, it would be gravity and the force as he collides with the ground. This is why you should always wear a seatbelt, because when you're wearing a seatbelt, right, and that force is applied to the car, the seatbelt applies that force to you because it's part of the car. That's why if your parents have ever stopped suddenly, right, and you go forward, that seatbelt locks in place. That's to keep you from flying out of the car, and that's applying that force to you. So here's another example of Newton's first law. So we have the skier, and in the animation of the skier, he continues in motion down the hill, right, until he's acted upon by an outside force. And in this case, it's going to be gravity, and then it's also going to be the friction from this unpacked snow on his skis is going to cause him to further slow down and eventually stop. And if you watch his speed coming down the hill, you'll see it's increasing, it's increasing, it's increasing, it's increasing. Here we go, it's still increasing. When we get here, right, it starts to decrease. So gravity, right, he's now at the bottom of the hill, and then we've got all this friction from the unpacked snow. So Newton's second law of motion states that an object's force depends upon the object's mass and the acceleration. So in other words, to move a mass, you need a force. So if you want to get this 1,000-kilogram car moving at 0.05 meters per second squared, so if you want to accelerate it to 0.05 meters per second squared, you would need to use 50 newtons of force to push that car, to get it moving to that acceleration. So let's look at some other examples. So we have 2 cars, the same car. One has an acceleration of 5 meters per second squared. The other car has an acceleration of 10 meters per second squared. They're both crash into this wall. The crash of the car that was moving at 5 meters per second squared is going to have less force than the car moving at 10 meters per second squared because it has a greater acceleration. Now, let's say our acceleration is the same, but our mass changes. So we have a dump truck and we have a smart car. The dump truck, and they're traveling at the same speed. The dump truck is going to hit the wall with a greater force than the smart car because it has significantly more mass. So if the dump truck hits the wall, it's going to cause much greater damage than the smart car, even if they're traveling at the same rate of speed. Here's another one. So we have you and we have a major league pitcher. So the ball is going to have the same mass. You're both throwing the same ball. The major league pitcher will have more acceleration than you will because he can throw the ball with more force than you can. So it works the same, like it works if you change whatever you're solving for. Let's talk about Newton's third law. For every action or force, there is an equal and opposite reaction or force. So this is what concept tends to be one of the most abstract concepts that we deal with. So if you have a book on a table, right, you have gravity is pushing down on the book. And the table is pushing up with an equal and opposite force on the book, preventing it from falling all the way to the floor. So gravity is pushing down on the book, keeping it from flying into space. And the table is pushing up on the book with the same amount of force, preventing the book from falling any further, falling through the table. So if we look at the girl also on the skateboard, and you could try this at home either with a skateboard or roller skates, so she's pushing on the wall with a force. The wall, in turn, is pushing back on her with the same amount of force, an equal and opposite force. So her force is going to the right, the wall's force is going to the left. And because of that, this skateboard is going to roll backwards. It's going to roll to the left of your screen because of that equal and opposite force. So let's look at Newton's third law in action. So when we have this person on the canoe, so when he jumps out of the canoe, he applies a force downward and backward. You can see the canoe go down a little bit, and you can see it obviously slide backward. The canoe, though, applies an equal and opposite force to him, pushing him upward and forward and onto the dock. So that's how he is able to get up in the air and forward, and the canoe, in turn, is going to go down and back. So what happens if the two skaters push off each other? If the two skaters push off each other, they're both going to go backwards in the direction opposite that they're pushing. If one of the skaters pushes the other, the skater that's doing the pushing is going to go backward. We can say the same thing for the air in a balloon. So if you blow up a balloon and then you let it go, the action is that the air is going to rush down out of the balloon. And the reaction is, so the air inside the balloon, is going to go down and out. And the air outside of the balloon is going to push the balloon up in the air. And that's why the balloon will go flying off, through the air. We can get an example here. So we watch these astronauts and what happens in space.
On March 18, 1965, Russian cosmonaut Alexei Leonov became the first human to float in space. Not to be outdone, the United States sent astronaut Ed White into outer space just 3 months later.
You're right in front, Ed. You look beautiful. I feel like $1 million.
He floated for 20 minutes and loved every bit of it. Floating around is fun and easy. The next American would have to do more than just float. Gene Cernan would try to find out if humans could do work in outer space.
I was going to go out and I was going to have to do legitimate work. I had to basically assemble a whole flying backpack outside the spacecraft in zero gravity through a nighttime cycle where I had little or no light.
Cernan was supplied oxygen from an umbilical hose that passed through an open hatch. His commander, Tom Stafford, seated inside, piloted the spacecraft. Cernan quickly discovered that handling even simple objects was extremely difficult.
Every time I'd push or turn a valve, it would turn my entire body in zero gravity. I had nothing to hold on to. And we take for granted gravity because we can do that kind of work with ease if something is holding our feet to the ground. Nothing was holding me anywhere.
Within minutes, Cernan was sweating from the extreme effort it took to control his movements.
Within a few minutes, he fogged over. We were so naive, we didn't even think about putting defog on our visor like you do when you go snorkeling or scuba diving. And so he was huffing and puffing, and I was flying the spacecraft. He says, Tom, I've got a hard time controlling myself.
And it was a very, in retrospect, somewhat of a hair-raising thing. And there were probably times where there were people down here on Earth wondered whether I'd get back in. My heart rate was running at 170 beats a minute.
I said, hey, this is not a good situation at all. So I called the ground contact, said, I've called it quits. I'm going to get him back in before we go into the next nighttime. Got him in. Finally, he just couldn't hardly move. And then when he opened his visor, he was absolutely pink, like he'd been in a sauna about an hour too long. The next day we landed, and they flew the suit right back to Houston. They had over a pound or a pound and a half of water out of each boot. But he lost, I think, 10 and a half pounds in 2 hours and 5 minutes outside.
NASA was now determined to find out what went wrong.
As engineers, we started saying, look, we've had 3 missions where the EVAs didn't go well. What was wrong? Then we had a science advisory team step in and say, look, your entire principles of EVA are wrong. How you train, how you prepare the crew.
Everybody forgot Newton's third law of motion. To every action, there's an opposite and equal reaction. And when they touched the spacecraft repelled them.
Although weight is reduced in outer space, the mass of an object is unchanged. To move a mass, force must be applied. Newton's third law predicts an equal but opposite reaction. On Earth, gravity would allow Cernan to gain a footing and counteract the reactive force. But in outer space, the reactive force sent him reeling. Having learned a difficult lesson, NASA's next capsule was built with special handholds and footholds to anchor the astronaut in place. Most importantly, NASA began training astronauts underwater, the closest environment on Earth to weightlessness. The new training and tools made a big difference for Buzz Aldrin, the next American astronaut to do work in outer space.
I felt that it was a piece of cake outside, just moving very slowly. There was no challenge. You decide that you're going to move in a certain way and you need leverage, so you just don't allow yourself to get out of position.